Temporal difference learning. In this section, we'll learn about temporal difference learning, Q-learning in Python, and Q-learning in one-step temporal difference method in R. Temporal difference learning. In this video, we'll talk about temporal difference learning. Temporal difference combines the Monte Carlo and dynamic programming. The Monte Carlo aspect is because there's no need for a model of the learning environment. Dynamic programming aspect is the bootstrapping updates which are available at each state of the incremental procedure. It's not good for systems with large spaces, and compared to previous learning methods that you've been exposed to, the prediction is at one step. So some of the advantages of temporal difference. Temporal difference methods combine basically the sampling of Monte Carlo with the bootstrapping of dynamic programming. They have an advantage over dynamic programming methods in that they do not require a model of the environment, like Monte Carlo. And its reward and next state probability distributions do not need to be known either. So basically we refer to temporal difference, or TD, and Monte Carlo updates as sample updates because they involve looking ahead to a sample successor state or state action pair, using the value of the successor and the reward along the way to compute a backed up value and then updating the value of the original state or state action pair accordingly. So sample updates differ from the expected updates of dynamic programming methods in that they are based on a single sample successor rather than on a complete distribution of all possible successors. The most obvious advantage of temporal difference methods over Monte Carlo methods is that they are naturally implemented in an online, fully incremental fashion. So with Monte Carlo methods, you have to wait until the end of an episode when the return is known. But with TD methods, the agent waits only one time step. So why is this critical? It's critical because some applications have very long episodes. So delaying all learning until the end of the episode is way too slow. Other applications are continuing tasks and have no episodes at all. So as we noted before, like in the Monte Carlo section of this course, some Monte Carlo methods must ignore or discount episodes on which experimental actions are taken, which can greatly reduce the efficiency of learning, and it can greatly slow down the learning. So temporal difference methods are much less susceptible to these problems because they learn from each transition regardless of what subsequent actions are taken. And the temporal difference, or TD error, at each time is the error in the estimate made at that time. So because the TD error depends on the next state and the next reward, it is not actually available until one time step later. Here we have the pseudocode for the tabular temporal difference one-step method. So as you can see, given some experience following a policy, the agent updates their estimate of V for the non-terminal states occurring in that particular experience. Whereas in Monte Carlo methods, you have to wait until the end of the episode to determine the increment to V. With temporal difference methods, you only need to wait until the next time step. So at the next time step, the agent immediately forms a target and makes a useful update using the observed reward and the estimated V. The simplest temporal difference method makes the update immediately upon transitioning to the state and receiving the respective reward. Because the one-step temporal difference method bases its update in part on an existing estimate, we say that it is a bootstrapping method like dynamic programming. So what about the SARSA method? SARSA method is an on-policy method, which, if you recall, on-policy methods attempt to evaluate or improve the given policy that is used to make decisions, and it's used as a control function when you're thinking about exploration versus exploitation. So here's some pseudocode for the SARSA method. The SARSA method is basically a way to use temporal difference prediction methods for the control problem. So as usual, we follow the pattern of generalized policy iteration, but only this time using temporal difference methods for the prediction. And as with Monte Carlo methods, we face the need to trade off exploration and exploitation And again, approaches fall into two main classes: on policy, which is the SARSA method, and off policy, which is the Q-learning method, which we will talk about shortly. The first step is to learn an action value function rather than a state value function. In particular, for an on-policy method, we must estimate the reward for the current behavior policy and for all states S in actions A. This can be done using essentially the same temporal difference method described for learning B. So if you recall that an episode consists of an alternating sequence of states and state action pairs, now we're considering transitions from state action pair to state action pair, and we're learning the values of state action pairs. So formally, these cases are identical. They're both Markov chains with a reward process. So the same theorems that assure the convergence of state values under the one-step temporal difference method also apply to the corresponding algorithm for action values. So basically, this update is done after every transition from a non-terminal state. And if the state is terminal, then Q is defined as 0. It's pretty straightforward to design an on-policy control algorithm based on the SARSA prediction method. And as in all on-policy methods, we continually estimate Q for the behavior policy and at the same time change the policy towards greediness with respect to Q. So Q-learning is a policy-based algorithm, and it's the off-policy method. SARSA is the on-policy, and Q-learning is the off-policy. And remember, all-policy methods evaluate and improve a policy different from the policy that's used to generate the data. So here's the pseudocode for Q-learning. And Q-learning is definitely one of the earliest breakthroughs in reinforcement learning. With Q-learning, the learned action value function Q directly approximates the optimal action value function, and it's independent of the policy that's actually being followed. So doing this dramatically simplifies the analysis of the algorithm. The policy still has an effect in that it determines which state action pairs are visited and updated. However, all that is required for correct convergence is that all pairs continue to be updated. So let's take a look at the pseudocode. You have to initialize the values table Q, observe the current state S, choose an action A for that state based on an action selection policy, take the action and observe the reward in new state, and update the value for the state using the observed reward and the maximum reward possible for the next state. And you do this until you reach a terminal state instead of the set of non-terminal states. You've learned about temporal difference learning. You've learned about one-step temporal difference, Q-learning, and SARSA. In the next few sections, you're going to utilize how to take advantage of the MDP toolbox for one-step temporal difference and for Q-learning.